about properties of ionic compounds, and then we're also going to look specifically at some properties of water as well. So ionic compounds and molecular compounds in general are going to be review, and then the water properties are going to be somewhat new. So ionic compounds themselves have this electrostatic attraction, which means attraction between a positive and a negative. Okay, cation being positive, anion being negative. It leads to a very stable crystal lattice, and that means that the solids will have a very high melting point. Just to flip down here, you can see kind of a slice that I've got here, where each sodium is attracted to the 4 chlorines around it, plus 1, if you can imagine, coming out of the screen towards you and 1 going into the screen. Okay, so in this slice you can see it, and then here's sort of a 3-dimensional picture where it's been built up. And again, we get this nice attractive force in between the sodium and the chlorine, sodium and the chlorine, sodium and the chlorine, sodium and the chlorine. And of course, this sodium that I'm drawing these up to would have another chlorine coming out and to the left, and another one going out and to the right. And that holds true for every single ion in there. It means that they have a very high melting point, because in order to melt, these ions have to get heated enough that they vibrate in place strongly enough that they will let loose and overcome that positive to negative attraction. That strong attraction also leads to the retention of crystal shape. So if you take a look at sodium chloride under a microscope, even after you've smashed it with a hammer, the little pieces of dust will still have cubic edges. And it might not be perfect little cube shapes, but the edges and the break points will be cubic. Ionic compounds are all at least slightly soluble in water. Now, that being said, some of them are it's very, very slightly, and you're not even going to hardly be able to measure their solubility. But all of them will dissolve at least a tiny bit. And this is due to the fact that water molecules themselves are slightly polar. Okay, we'll talk about that in a bit, but that polar bit means that one end has a partial negative charge and the other has a partial positive charge. Okay. Again, more on that later, but if we were to look here, if you've got chloride, which is negative, close to a partial positive in water, that positive from the water pulls at the chloride just a little bit. And then this sodium next to it is going to be attracted, pulled a little bit by the the partial negative in the water. Okay. Now, ionic solids do not conduct electricity, but because they dissolve in water and form ions, solutions of ionic compounds will conduct electricity. And the higher the concentration, the better they will conduct. Okay. Now, molecular compounds, they're held together strongly within molecules, but the molecules themselves only weakly hold together. Okay, so if you've got oxygen gas, for example, or nitrogen gas is diatomic, and so we have a nitrogen that's actually got 3 bonds, that's Chem 20 stuff, between that and another nitrogen. Now, between the 2 nitrogen atoms in each of these molecules, they're held very strongly together. It's difficult to break this set of bonds here. To do anything to get this to break apart is going to be challenging. It's not going to happen easily. However, this atom here and this atom here can't really care less about each other. They are not going to be well attracted to each other, and that's true of all molecular compounds. This means that most molecular compounds will have at least relatively low melting and boiling points. Okay. Now, molecular substances can form crystals, but they're typically fragile and they don't hold their shape. Solutions of molecular compounds do not conduct electricity, and nor do molecular solids for that matter. So what are some examples? Well, I've given you an example of a sodium chloride as an ionic compound. Okay. A molecular compound, an example might be sugar. Table sugar is one good example there. Nitrogen gas is another one. Okay, if we were to cool it down below minus about 200 or so, nitrogen gas will actually form a solid. It wouldn't conduct electricity. Okay. Sugar, as a solid, it doesn't conduct electricity. Sugar, as a solution, does not conduct electricity. Now, water is a molecular compound, but water is weird. Okay? It is itself a polar, slightly bent molecule. Now, water, remember, is H2O, which means there's H2O. It means there is one oxygen, and it's bonded to two hydrogens. Now, shape-wise, oops, let's try that again. Shape-wise, it's going to look something like this, where there's an angle between the two hydrogens, and the oxygen itself is kind of at one end, if you can imagine a little triangle. Sometimes if we draw the atoms as little spheres, people will draw it sort of looking like a little Mickey Mouse head. We have an oxygen and we have two hydrogens off here, right? These are each our hydrogen. And this is our oxygen. Okay. The oxygen end of this, and you'll talk more about why this is, for Science 10 though, you need to know about just what's going on. You'll talk about the why part of this in Chem 20. The oxygen end is a little bit negative, and each of the hydrogen ends are a little bit positive. When a molecule has this kind of an arrangement where part of it's negative, part of it's positive, we call it being polar. Okay. Shape-wise, it's slightly bent, and that's this little angle here. We'll talk again more about why that is in Chem 20. Now, water molecules in a liquid or a solid are held together by hydrogen bonds. Now, a hydrogen bond is a special type of attraction between two different molecules. And basically, it's going to happen because it's this polar. Okay? Positives and negatives attract each other. You should remember that from Science 9. Each of the hydrogens is a little bit positive. Each of the oxygens is a little bit negative. Hey, this negative can align itself so that it's close to this positive. And that makes it so that there's going to be some attractive force. It helps to hold things together. Now, practically speaking, in like the physical world that we can see around us, what this does is it raises the boiling and melting points from similar compounds that don't have these types of hydrogen bonds. What I'd like you to do right now, really quickly, pause the video. Well, when I tell you what to do, pause the video, and I want you to look up. That's not working. Pause the video. I want you to look up, using Wikipedia is just fine, melting points. Actually, go for boiling points of H2S, hydrogen sulfide, H2SE, hydrogen selenide, and H2TE, hydrogen telluride. Look those up, record them on your piece of paper, and then compare them to water. Now, water, of course, melts at 0 degrees Celsius and it boils at 100 degrees Celsius. This is a much higher temperature, and you're going to see that, than these other compounds. Now, water, as it cools and begins to form ice, these molecules that in a liquid are sort of randomly moving around next to each other spread out into a 3D array that contains 6-sided rings. What this does is it decreases its density, and that means ice floats. Okay. So here we can see another picture of why sodium chloride would dissolve, now that we've looked at the fact that water is polar. Okay. So the negative end of the oxygen is attracted to the positive part of the sodium. The positive end of the molecule with the 2 hydrogens is attracted to the negative end of the chloride. Okay, now when we look at water again, here we've got a lovely picture of some clouds where we can see water as a gas. The molecules are spread far apart. Okay, not much attraction between them. In a liquid, they're close together, and they will generally align themselves so that these little white hydrogens are close to another oxygen. And then we get to a solid. They actually move apart from how they were in a liquid, and they form these lovely 6-sided rings. And if you ever look at a snowflake up close, you will see that it has some kind of a 6-sided structure. That's where it comes from.